Hello, I'm Laura Cassidy from the American Chemical Society. Welcome to this media briefing from ACS Fall 2021. We're joined today by Dr. Gellert Mezei from Western Michigan University. He's developing nanojars that capture dissolved carbon dioxide and toxic ions from water. Dr. Mezei?
Thank you, Laura, for the introduction and for the opportunity to present our research done here at Western Michigan University. We have developed a new class of anion binding and extraction agents that we termed nanojars. Before presenting our nanojars, first I'd like to explain what anions are and why we are interested in binding and extracting them from water. Anions are charged molecules. Common examples include chloride, fluoride, hydrogen carbonate, sulfate. These are commonly found in our drinking water. They are also found in living organisms. They are vital for the healthy functioning of living organisms. Some other anions, however, such as arsenate, chromate, should never be found in our drinking water, as they are highly toxic. They can cause diseases, cancer at low concentration, as well as death at high concentration. Therefore, it is essential to remove such anions, not only from our drinking water, but also from any natural water bodies, because they are also harmful to plants and animals. Some other anions are used on large scale in industry or agriculture. For example, phosphate, nitrate are used as fertilizers. These anions can accumulate in water bodies and lead to eutrophication, which basically is the death of most life forms present in the respective water body. Yet another aspect of anion extraction is recovery and recycling. Anions such as phosphate, which is an essential fertilizer, are mined as phosphate rock. This is a finite reserve, just like petroleum. So once all the phosphate rock deposits are exhausted, we have to resort to recovering phosphate from diluted media, mostly large water bodies, such as the Everglades in Florida. Um, Uh, how, how do we extract anions from water in general? There are several commercially available methods for extracting anions, uh, each with its advantages and disadvantages. Most of them rely on binding the anion to a solid surface, from which the recovery of the anion can be challenging. We propose a different method for binding anions using liquid-liquid extraction, wherein the nanojar, the anion extraction agent, will transfer the anion from water into a water immiscible organic liquid, from which it can be easily recovered and recycled or disposed of. On my first slide, I will explain what nanojars are. So nanojars are made up of three components. An organic molecule called pyrazole, copper 2 plus ions, and hydroxide ions. When mixed together in an organic solvent in the presence of certain anions, they form macrocycles or rings of different sizes, from 16-membered up all the way up to 14-membered. Shown here are the 6, the 9, and the 12-membered rings. 3 of these rings bind together to form a nanojar. In this case, the 27-membered nanojar. On my next slide, we can see a top view and a side view of the 27-membered nanojar. We have made nanojars based on over a dozen different ring combinations, ranging in size from 26 to 33 membered. The name nanojar comes from the shape and the size of these assemblies. Nanojars resemble containers or jars, which have a central cavity where they bind the anion very strongly. As shown, actually, the jar is upside down in the side view. They are 2 nanometers in size with the parent pyrazole ligand without substituents on it. We can also functionalize nanojars by attaching various functionalities that allows for the tuning of different properties of nanojars, such as solubility, selectivity. We can attach fluorescent moieties, so we can prepare fluorescent nanojars. Nanojars are very robust thermally, so they can be used in a wide temperature range. They are very resistant to high alkalinities, but they are sensitive to acidity, which actually allows for their recyclability. On the next slide, I will explain some of the challenges encountered with anion extraction. First, small inorganic anions, such as the ones discussed here, love water. They bind very strongly to water because they are charged, and water has a large dipole moment or large charge separation within the molecule. The larger the charge on the ion, the stronger the ion binds to water. The doubly charged carbonate, for example, is much stronger bound than the singly charged bicarbonate. To extract anions from water, we need to break these strong bonds and transfer the anion into an organic receptor. Very few organic or metal organic receptors bind doubly or triply charged anions stronger than water. Interestingly, nanojars not only bind doubly and triply charged ions extremely strongly and easily extract them from water, they also bind doubly charged ions stronger than singly charged ions. Now, this brings me to the next challenge in anion extraction, selectivity. In some instances, we need to selectively extract a specific anion from a mixture of different anions. Nanojars have total selectivity for doubly or triply charged anions, such as sulfate, carbonate, phosphate, over singly charged ones, such as nitrate and chloride. We achieved further selectivity by tethering pairs of pyrazoles together. Thus, by tuning the length of the tether, we can change or switch the selectivity of nanojars for either carbonate or sulfate, which are both strongly bound by nanojars, and they are both they can be selectively separated by using the different tether length. Finally, I would also like to mention a new direction in nanojar research, that is carbon dioxide sequestration. We are all aware about the alarmingly high concentration of CO2 in Earth's atmosphere. We also recognize the need for removing some of that CO2 to avoid possibly catastrophic effects on the climate. Most carbon dioxide capture efforts are directed to air, but there are also large amounts of CO2 dissolved in water. After all, 71% of our Earth's atmosphere is covered by water, and there's approximately 150 times more or higher concentration of CO2 in seawater than in the air. Nanojars can pick up the tiniest amounts of CO2 from water. Therefore, anions can be a very efficient CO2 sequestration agent. Also, although from water, not directly from the air. To to sum up, I'd like to thank the students that worked on this project. I'd like to mention two outstanding PhD students, Basil Ahmed and Wissam Ali Savi. I'd like to thank all other people who contributed to this project, the National Science Foundation for funding, and I'd be happy to answer any questions you have.
Thank you, Dr. Mezei. I'd like to ask you a few questions about your work. First of all, what gave you the idea to develop nanojars?
Nanojars were discovered serendipitously. No one can really design such a large architecture. We were working with smaller copper pyrrolate structures. And when the conditions were right in the reaction mixture, nanojars formed. Once we discovered them, we recognized that they can bind anions, and that's how we started developing them into anion extraction agents.
Very good. And what do you think are the most promising applications for nanojars?
Definitely for removing even very small concentrations of doubly or triply charged anions from water.
Okay. And how could a body of water become contaminated with these anions, such as chromate, sulfate, or arsenate?
There are both natural and anthropogenic sources. Most of the arsenate usually comes from natural sources. In some areas in the world, there are higher concentration of arsenic containing minerals in the ground, so that gets into the groundwater. But there are many industrial sources. Chromate, that's not natural, that's used in industry, and arsenate is also used in agriculture as pesticide in some places. So there can be some man-made sources of arsenate as well.
Are there methods that are currently used to remove carbon dioxide or carbonate from water?
There are some being developed for sure. Currently, there is no method that is feasible for removal of CO2, either from air or from water on large amounts. The ones we need to reverse climate change. It will take a lot more research to get to that level, to deal with the billions and billions of tons of CO2 we need to remove annually.
Sure. Could nanojars be added directly to bodies of water, such as lakes, or would the water need to be pumped into some kind of a treatment station?
Yes, so we don't want to leave nanojars in water. Nanojars actually don't dissolve in water. In the liquid-liquid extraction system, they would dissolve in the organic layer, which sits on top of the water layer. We would mix the two together. The organic layer separates from the water layer. It will contain the nanojar and the anion incarcerated inside the nanojar. So then we would separate the organic layer, recycle the anion from it, as well as the nanojar, which can then be returned for extracting fresh amounts of the anion.
Okay.
So yes, we would need some setups for pumping water out from a water body and then releasing it back.
Okay. And how do you separate the treated water from the organic phase containing the
It separates
nanojars?
naturally.
Do
So
you kind of pump it off or
it's
suck
like
it off?
oil, it's like oil and water that don't mix. We
Yes.
can shake it up so there's contact between the two, but once we stop mixing, the two separate naturally. So then we can just decant the organic layer from top of the water layer.
Okay. All right. And when you add the organic solvent containing the nanojar components to water, how long does it take to trap the carbonate ions?
It's very quick. It's basically instantaneous. These nanojars are hungry for carbonate.
Okay. Do you think it's feasible to treat enough of the world's water with nanojars to capture sufficient carbonate to have an impact on climate change? And would you have to treat, all major bodies of water, including oceans?
Yeah, well, this is something for the long term. So we have just discovered this possibility of eventually removing CO2 using nanojars. So it will take several steps to get to a level large enough to mitigate global level crises, such as either CO2 in the atmosphere or removing contaminants from water. So we are not there yet, but we are definitely working on it. And we are also working on converting the captured CO2 into possibly useful chemicals, or fuel, or as we call them, value-added products. Now, to treat all the CO2 in Earth's atmosphere and all the oceans covering the Earth, it will probably take different methods. So it will not be just one single method that will solve all the problems.
Okay. And you mentioned possibly being able to recycle the carbonate and the other anions into useful products. What are some examples of these products?
For example, what we would really like to do is transform CO2 into fuel. We still do rely on fuel, liquid fuel, mostly. There is a lot of research towards getting rid of fossil fuels or fuels that emit CO2 in the atmosphere, but currently we can just simply switch to all electric, all wind. So for some time we will have to keep burning fuels. So that's one very desirable product that can come out of CO2. We can convert CO2 to solvents used in industry for extractions, for example, for the extraction we would be doing. There are many other uses. And basically, carbon dioxide contains the building block for all organic molecules. Right, so under the right conditions, CO2 can be converted to almost any organic compound in a number of steps.
Great. So what are your next steps for this research?
We need to make these nanojars even more selective, because usually when we apply anion extraction, we have a mixture of different ions present in solution. And we usually are interested in removing only one or two particular ions. Sometimes the other ions are in a much higher concentration than the anion of interest. So if the nanojars were to extract everything that is present in that mixture, it would not be very efficient. So we need to make them much more selective. Actually, we first had in mind selectivity for sulfate before we came to realize that actually carbonate, which is not toxic, but it can be used for removal of CO2 from the atmosphere and then indirectly from the water. Suddenly this became of interest as well.
To conclude, what do you want viewers to take away from your talk? What's the key conclusion or take-home message?
I would say that we always need to keep an open mind. And we sometimes start out looking for something, and then on the way, sometimes we do get to where we want to get, sometimes we don't. Then we can often find new directions and new uses for the compounds we are preparing. I think that's the most exciting part for the students working on it as well, because we constantly discover new things which are not related to anion extraction, but to a variety of different aspects of chemistry. And whenever we come across something like that, we like to explore that route. And by doing that, we were able to prepare green technologies. We were able to answer theoretical questions that were not understood before, etc.
Very good. Thank you. Media briefings for ACS Fall 2021 will be posted throughout the meeting at www.acs.org/ACS Fall 2021 briefings.